the definite integral. So last time we kind of ended with looking at sigma notation, going from 1 to n. And we said that this is called the Riemann sum times our change in x. So, and then we looked at, as we add those up more and more, as we look at those rectangles, we have this little bit extra here, or sometimes we might have maybe under a little lower, right? We're missing that. And then so we said, so if we increase this number with this n number of rectangles, we keep on increasing it, you know, we're looking at the limit of it, and then that gets smaller and smaller and smaller. So as long as we increase that n, we can actually get that true area, right? So that area underneath the curve. And so what this turns out to be is called the definite integral. And so there'll be some little bit of switching on notation here from the limit of the Riemann sum, or Riemann sum, however you want to say it, or however it's supposed to be said. I just say it wrong probably. And so what this usually tells us, like we've already figured out, is area and distance, and some distances and some lengths. It can also give us volume, center of masses, It can also give us work, which we'll talk about. Those are kind of the harder problems to deal with. So it can do a lot of different things, this definite integral. It just has a little bit of different notation, so we'll kind of get into that. And so when we switch to this definite integral from a to b, so it is still, that's why it's definite, because it is on an interval, right? So it's definite, it's within a certain space, right? It doesn't go on for forever. And so it's from a to b, just like our a to b, in order to find our change in x. It's that same a and b here. So our a and b go in this, and I'll go ahead and take this apart. This sign right here is called the integral sign. The dx, that's basically our change in x. The f of x, that's our function. So those are very similar. These are very similar, or these are the same thing. And then just this integral sign and the limit, those kind of just exchange places, right? So in this, again, it only works if the limit exists as well. So a and b, those are a and b, and b. A and b are limits of integration. And f of x, that's our integrad, f of x, integrad. And we have dx, means the variable in terms of x. And it's the same thing as our change in x. And the xi, and sometimes you'll see this, those are just sample points. Like right when we plugged in 1, and then we plugged in 2, and then we plugged in 3, you know, for our x's in order to get our y values, right? So that's very similar. And one big thing that you want to understand too is this does not mean the integration symbol. That's the integral sign, but this whole thing right here is the integration symbol. So it's the integration symbol from a to b. Okay, so the whole thing is the integral symbol. A lot of times, you know, you'll see me leave this off until the very end sometimes, and then sometimes I'll leave this a and b out to the very end. That's just me being lazy, because I don't want to put those numbers in, so I just kind of wait till the thing's over. So like I said, we have the Riemann sum, and there it is when we take the limit of it. And so when it's, sometimes we've only looked at so far, like when our graphs are above. Well, eventually sometimes it might be above and below, So we have above the x-axis and below. And so what we do is to find, we just calculate this, and the net area is the definite integral. So you just take the one above minus the one below. So we take the area of this minus the area of that. Integral, definite integral. So for example, if we're doing from a to b here, so a is 0 and b is 5 of this definite integral, then we go ahead and take, so about 2.5, it kind of crosses there. So if I move my b down to 2.5, right about there, so that area is about negative 5.97. So negative 5.97, and then if I move that over, I guess, and then this area, so that would be the area above the x-axis. So that is 17, 17 or so. Then from A to B, the total area is just going to be that difference of that. Okay, so, and this is kind of rounding a little bit here. So you have negative 6 and 15. 15 minus 6. It's a little bit off just because the 8.95, just because the upper and lower limit. This one is an overestimate above here, and down here I was an underestimate, so that's why the difference between, you know, the 15 minus 6 was not 9, right? It's because this is kind of an overestimate and this is an underestimate. But if I increase the number of n's, then it will be really similar. So here the total area still is 8.95. If I move this down 2.6-ish, so it's negative 6.75, and I move that up, then it's 15. 15 minus 6, that's around our 9, right? So that's a better estimate. So that's how you find, that's the definite integral. So the definite integral is the whole entire area of that from 0 to 5. So it's the bottom underneath the x-axis minus what's above the x-axis. So our area is 8.95, and that's the definite integral. So now when you're asked to evaluate this, what you're going to be doing is you're going to be switching forms, right? Going kind of back and forth, but mostly I'm going to give you this one. So this one, and then you're going to be asked to transform it to that one, and then we go ahead and, just like we use the sum of sums, the sigma notation in the last video, we would use the same thing here. So we'd go ahead and expand this in order to answer it, right? So we'd take our function, that function would pretty much be the same thing. We just, instead of x's, pretty much we bring in i's, and then our a to b, we'll use our a to b to find that change in x. Okay, so we'll find that to find that change in x, and then eventually we'll take the limit of it to solve for what that number will be. But we're going to use our summation formulas, the ones that I gave you in the last video, or that you can find in the book. So we'll use those summation formulas and properties in order to separate it into shrink in order to solve this definite integral. So the only thing that we really have to do some work here in order to switch it forms, because basically this gets replaced, the summation, or sorry, not summation, the summation, yeah, the summation and the integral sign gets replaced. All right, so those switch places. The f of x and f of xi kind of get switched places. They're just still talking about the function. And so the only thing you really have to do is find that change in x, which we've done plenty of times by now. And then there's a new thing, this xi, because this is x and this is xi. So that xi we can find by just taking x and adding our I times change of x, right? Because as i's change, as I starts with 1, our first x, you know, if we go from the right hand side, is a plus 1 change in x, and then if I do a 2 for my I, that would be 2 change in x. And so remember, that's how we find we start at a, and then this one would be a plus change in x, and this one would be a plus 2 change in x. Right, remember that's how we found our x's. So we'll have to just pretty much just do these two pieces of x. And what you'll do is you'll pretty much be given the a and b, so you're good there. The n you'll leave as n, and so that means this thing you just have to switch in the a and plug in what this number is, and this change in x will have the n in it, and we'll evaluate it like that, and then eventually we'll take the limit at the very end. So let me go ahead and just do one example for you. All right, so let's go ahead and practice one. And so we're finding the different integral from 0 to 3. So we want to find that change in x first. So that's b minus a all over n. So that's 3 minus 0 over n. We leave n as n. So this is 3 over n. And the next thing we want to find is xi, because then we can start replacing stuff. So this is a plus I times the change in x. So the change in x we know is 3 over n. So times that by is just 3i over n. And our a is 0. So that's our change in x. So now we can start replacing this. This integral sign is the limit as n goes to infinity. Most time I'll leave this off until the very end. And then the sum formula, and I usually leave this I equals 1 to n off too, just for writing purposes. I don't have to write that much. And then I can substitute x for xi. So this is 3i over n cubed minus 6 times x, which is now going to be xi. So 3i over n, and then times by our change in x, which is just 3 over n. So 3 over n. Okay, so that's what it looks like. Substitute it in. And now we can go ahead and evaluate. We can bring this 3n out front of the sum. So 3 over n in front of the sum. Distribute my power. So this is 27i cubed over n cubed and minus 18i over n. So that I'm finding the sum of that. Okay, so now I want to rewrite this basically so I get my i's kind of by themselves, or I cubes or I squared, and then we can use our sum formulas. Okay, so now the limit n goes to infinity, 3n over the sum of 27i cubed over n cubed. Then I can apply the sum of a difference is the difference of the two sums. Okay, and then I can go ahead and take out my constant, so 27 over n cubed I can take out, and 18 over n I can take out. So 27 over n cubed and the sum of I cubed. So now I can substitute that formula, and 18 over n times the sum of just I. So I can substitute a formula there. And again, I'm taking the limit, but like I said, a lot of times I'll just leave that out until the very end. Okay, so now we know this formula. This is n times n plus 1 all over 2, and that's being squared, and this I is just n times n plus 1 all over 2. All right, so there's the formulas. Substitution. Still have 27 over n cubed there, and this whole thing is being raised. I guess I don't need that one. To the 3. It's not being raised to, it's just being times by 3 over n. Okay. Now before I take the limit, I want to simplify all this. So I'm going to use my exponent rules. This is n squared. This is n plus 1 quantity squared. This is now 4. Cancel these. This 2 and this negative 18 is going to be reduced. So I get that. That's kind of nice on this one. And now I can simplify this one as well. This can cancel out. Let's do blue. That will cancel out with that. Can't cancel out that 2. I guess, sorry. Leave that as n. Leave that as a cube for now. Okay, now it's here. Let's go ahead and now we can simplify this one. Okay, so this becomes basically 27, 4 can't cancel. So it still says 27, but these 2 can cancel with 2 of those. And this is a quantity squared, right? So if I have to FOIL that out, okay, and then just 4 and on bottom. I still got my 3, the limit as n goes to infinity of 3n times both of these. So I can distribute that 3n now. So let's distribute that 3n. That's 81 over 4 and n squared on bottom. So we have n plus 1 quantity squared over n squared. Okay. And then minus 27 over n plus 1 times n plus 1 all over n. All right. Now we can do some tricky little things before we take the limit. We can rewrite these. So this is squared, so that's n plus 1 times n plus 1. And then when I'm multiplying, I can separate it, that division. I can put 1 n underneath here and 1 n underneath here. That'd be an n squared. Kind of like this one to the right, because I want to rewrite this one to the right. Whenever I have a plus b over c, I can separate that to a over c plus b over c. So two separate fractions instead of one. So I'm going to do that. I'm going to take n over n plus 1 over n. Because now I can reduce this one to 1. 1 times negative 27 is just negative 27 plus 1 over n. And then this one will do the same thing as this one over here. It will be 1 over, or be 1 plus 1 over n times 1 plus 1 over n. Right, both those will turn to that same thing. And then this one has 81 over 4 in front, and we're still taking the limit as n goes to infinity of this. Okay, so that's our kind of trick with that. And why we want that is because now when I take the limit of this, so I can distribute that limit in there, right? That limit is same kind of rules. We'll go to a constant. We'll go to each one of these basically as we substitute that in. All right, actually we can probably pull that constant out, which is fine. But as I put n in, when I put a big and bigger n into these are all going to go to 0, right? So this will go to 0, this will go to 0, this will go to 0 as I take the limit. Remember the limit rules, when I take the limit of a constant, it just stays as a constant. So this will be just 1 plus 0 is 1, 1 plus 0 is 1, 1 times 1 is just 1, 1 times 81 over 4 is just 81 over 4. And so there's my constant, limit of a constant still a constant. This will be just negative 27 plus 0, it's just negative 27. So this is negative 27. Find a common denominator, or just reduce that, right? Because that's just what 27 reduced is, or 27, put a 4 underneath here, have to times this by 4. So that's just, what? 106 times by 2 is 54, 108. So minus that, we get negative 27 over 4, which is like negative 6 point something or other. All right, so there's our answer. That's our area of this. So it's negative, so that means if I had the graph of it, it might look something like that. Then that means that maybe here, it'll probably be backwards. Probably be something like this to here, from here to here, say. And so this is underneath the x-axis. It has more area than above the x-axis because it's negative. So there's the definite integral. So if I was writing this, I would say integral from 0 to 3 of x cubed minus 6x dx is equal to negative 27 over 4. So there's an example for you. Oops, there's an example for you. I guess not quite done, but the very last thing that I want to talk about was sometimes if you want to find the integral from a to b, or definite integral from a to b, and it's easier to find maybe something in between. So that means that the integral of this from a to c plus the integral from c to b will equal the full integral from a to b, which you can kind of see in this diagram. It kind of makes sense, right? It's just like the angle theorem. If this is a or angle or line segment theorem, right? And I have c, this section plus this section will equal the whole section. Same thing with integrals.